Okay, so this is a small introduction to some statistics that you would commonly see in studies as part of evidence-based practice. So just a little reassurance, not to panic too much. We don't expect that as a result of this you'll be able to learn or remember by rote all the calculation methods that are used here. That's not critical really. But what is useful is if you have a rough idea of what the numbers mean in the context of the study itself. So for example, you don't need to know how miles per hour is necessarily calculated to understand whether you're speeding or not. You just need to know what speed you're going according to the dashboard on the car and what the speed limit is for the road. And as long as you're under that speed limit, you're okay. So in the same way, with the statistics that you'll see in many papers, if you've got a rough idea of what they mean or how they should be interpreted, then you can tell to at least to some degree what's going on with the study results. So the common results of studies that you're likely to see will include things like absolute risk, relative risk, the number needed to harm or the number needed to treat, and the odds ratio. So we'll just go through those one by one to give you an idea of what each one means. So in our fictional example that we've referenced earlier, we have the results from this imaginary perfect study that's been done. And this talks about whether using a mobile phone will mean that your ears drop off. Now, of course, this is fictional. No mobile phones were harmed in the making of this study. But notice that out of the group that we got to use a mobile phone, here, that quite a high proportion of those lost their ears compared to the group that hadn't used a mobile. Here, it seems like there's a lower proportion that lost their ears out of the whole. So this is fairly easy to interpret because the groups are exactly the same. There's 100,000 in each group. But what if the numbers were different? What if there was a different number in each group, as commonly there is? How would you make sense of the data, and how could you display those findings? Well, that's where these different measures come in. So again, just looking back to how a cohort study is designed, we start off with a group right at the beginning here, and we've got one group here which was exposed to the mobile phones, and another group here which was not exposed to the mobile phones. And we follow up these two groups over time, and you'll notice that over time, when we followed them up, we found that the group that were using the mobile phones here seem to have lost more ears than the group who weren't using mobile phones. So that just gives you an idea of how that diagram works. So let's keep that example in mind, and let's think about risk. So when we talk about risk in statistics, the risk of something happening is a similar word as just the chance of an event happening. And it's calculated as the number of events as a proportion of the total in the group. So when we talk about risk, we might talk about risk in everyday language, like what's the risk of you being run over by a bus, for example. Well, that's the chance of that event happening, isn't it? But you can also use the word risk in a similar way for positive events. So, for example, what is the risk of you winning the lottery if you buy a lottery ticket? In other words, what is the chance of that event happening? So you can use that the word risk in that positive or negative sense. Now, when we talk about the absolute risk, let's see if we can work out what the risk of losing your ears is with the data that we've had in our imaginary perfect study. So if you were using a mobile phone in that study, the risk of you losing your ears was 20 events where people lost their ears out of 100,000 in the whole group, or 0.0002 or 0.02% of people lost their ears who were in the mobile phone group. Likewise, the people who weren't using a mobile phone, 5 out of 100,000 of those still lost their ears. So there was a baseline risk, if you like, even without using the mobile phone, of 0.005% risk of losing your ears over time. So what we have is an absolute risk increase of 0.015%. In other words, one baseline risk is taken away from the risk of losing your ears. So, in this study, you are 0.015% more likely to have your ears drop off if you use a mobile phone. Now, when you look at that absolute risk increase, you probably feel fairly safe and happy about using these phones after this imaginary study. But there is another measure, which is the relative risk. And the relative risk is calculated differently. Instead of taking one risk away from the other, we are dividing one by the other to give us a ratio. In this case, we see that 0.02 is 4 times bigger than 0.005. So our relative risk, which is the ratio between these two risks, one divided by the other, is 4. In other words, you're 4 times more likely to have your ears drop off if you use a mobile phone, according to that study. Now, of course, if someone that said that to you, you'd start getting worried. But what's interesting is that this 4 times more likely relative risk value doesn't tell you the whole story. It only gives you the relative risk. You still need to know what the baseline risk is to start with, which is here. So 4 times more likely compared to this very low baseline of 0.005, or only 5 out of 100,000 people, is not a big increase. It sounds like a big increase because 4 times sounds big, but 4 times a very small amount is still a small amount. So you need to know what your baseline risk is first when you're looking at a relative risk calculation. So why is it important to understand the difference between absolute and relative risk and baseline risks? Well, the answer is, when you're writing a paper, you'll often see that people will put the biggest, flashiest, most significant headline-grabbing number in their paper. Why? Because they want to naturally show off the results of the paper. So, for example, if I was to say I can give you 50 pence or £1 or £1.50 off a curry, you might not feel that that's a huge amount. But if I said we're giving a 25% discount off a curry, that might make your mouth water a bit more. It's a bigger number. Whereas if I said I'm going to give you a 1% discount on a high-end sports car, you might not think that sounds like a lot. But if I said there's £500 off a sports car, that sounds like a bigger number. So the stat has been used to give the best result. Now, we see this in advertising all the time. Would we see it in a peer-reviewed journal? Well, why not? Publish the bigger number, get the best, biggest looking effect. So you need to be careful when you're reading a study not to be drawn in by the initial numbers, just in case they're slightly less than substance. Look at the baseline risk, and in particular, look at the absolute risk increase or decrease in relation to the baseline. And that's where the number needed to treat and number needed to harm comes in. These are very useful numbers because they translate that kind of risk and probability factor, if you like, into a slightly more meaningful explanation. They're calculated as the inverse of the absolute risk increase or the absolute risk reduction. So in this case, we're looking at harm events, as in your ears falling off if you use a mobile phone. So we would use the number needed to harm. So the number needed to harm, the inverse of the absolute risk increase in this case, would be 6,666. In other words, if we gave 6,666 people a mobile phone, then one of those would have their ears drop off compared to if they didn't have a mobile phone. And the comparison is important because the absolute risk reduction, or the absolute risk increase in this case, has to come from the baseline as a starting point. So that gives you a little bit more information, doesn't it? So if you were telling someone that the number needed to harm was 6,666 for using mobile phones and having your ears drop off compared to not using a phone and having your ears drop off, that doesn't sound too bad. And of course, with number needed to harm, the higher the number, the better. But number needed to treat is a different thing, isn't it? So ideally, if a treatment is very effective, for every person you treat, they will get an improvement. They would benefit. So a number needed to treat of 1 is great. So for every 1 person we treat, that 1 person will get better. But with some drugs and some therapeutic interventions, the number needed to treat is higher than 1. So obviously, if we had a number needed to treat of 6,000, what we're saying is we would have to treat 6,000 people for 1 person to get better. Well, that doesn't sound so good, does it? Particularly when you're talking about some drugs, because every drug has side effects, 6,000 people will be exposed to the side effects of that drug. Not quite so good. So with number needed to treat, a lower number is better. 1 would be awesome. With number needed to harm, obviously, you want to have a highest number as possible because you want to harm as few people as possible. Just remember, when you're looking at number needed to treat or number needed to harm quotations, there's some things that you must see. First of all, you must see the comparator. Compared to what? In the instance we've got using a mobile phone compared to not using a phone. We need to see what the therapeutic outcome is. In this instance, the therapeutic outcome was having your ears drop off. Now that's a bit simplistic. We'd need to know the time period as well. Not only the duration of the treatment, but the duration of the follow-up for the outcome. And we would want to see the confidence interval, which we'll talk about confidence intervals in a bit. Now, with cohort studies and RCTs, you're starting from a population and you're sampling from that to cohorts and you're following them up over time after exposure. But with a case control study, that's an observational study. We haven't done an experiment. We're just looking at a group of people who happen to be diseased. In this case, this group of people has had their ears fallen off, and this other group of people here has not had their ears fallen off. Now, some of these people in each of these groups have been exposed to mobile phones, and we're looking at the losers, if you like, the bunch of losers here who've lost their ears, and what proportion of those were using a mobile phone, and we're looking at the bunch of winners, if you like, here, the ones who've managed to keep hold of their ears, and we're seeing what proportion of those have used a mobile phone or not. It's a different type of study. So a risk ratio isn't the correct calculation, but an odds ratio would be useful here. Now, what's the thing with odds is they're calculated differently. So like a gambling term, and it talks about winners and losers. So it compares the number of events to the number of the free from event. And the calculations give a similar result in many instances to that of the risk calculations that we've seen already. So the odds of your ears falling off when using a mobile phone is 1 out of 4,999. And the odds of the ears falling out of not using mobile phone, again, winners and losers, is 1 out of 19,999. So you will come across something which is called the odds ratio, and that's the difference between the two odds of two groups relative to each other. Now, there's no such thing as an absolute odds difference. And we did see a relative risk, an absolute risk increase, and an absolute risk reduction. We saw you could take away one risk from the other to get that, but you can't do that with odds. But what you can do is look at the ratio of odds one against the other. Now that's difficult to interpret. Oftentimes it's very similar to the risk ratio, but it's not always the same. So you notice that the ratio between the two odds that we've got here is 4.0006, which is similar to, but not quite the same as the risk ratio. So oftentimes you can interpret the odds ratio in a similar way to the risk ratio, but be aware that they will interpret differently, not always the same, and in some cases they can vary quite wildly. Now, when you're looking at odds ratios, and indeed when you're looking at relative risk, which is the ratio between two numbers, if the odds ratio or the relative risk is 1, then there's no effect. That means that the treatment is the same as the intervention. There's no difference. The treatment is the same as the control. There's no difference between the control and the treatment. So in our case here, our odds ratio was 4. People with no ears are more likely to have been exposed to a mobile phone. Now you notice that when we're looking at odds ratios in an observational study, we've started off with the disease, if you like, or the outcome, and we've worked backwards to say what was the exposure, because odds ratios work that way round. Whereas risk ratios work forwards, if you like, and odds ratios work backwards. Okay, just a little bit more statistics. Let's have a think about the play of chance. So, if you have a coin, take it out your pocket and flip it. Flip it 4 times. Now, how many heads do you get? You might want to pause at this point, have a go at that, and see what the results are in your group. So you might have found out that your coin might have given you 1 head, 2 heads, 3 heads, or maybe even no heads, or even 4 heads out of 4 coin tosses. Which is interesting, because most people would assume that a coin is a 50-50 chance of coming up heads if you flip it. And that's true. But chance can affect the result that you get. Even if you flip a coin 50 times, as Ken White did on his coin flipping page, you can put in the number of times you want to flip a coin, and the computer will simulate the coin toss for you, which saves you a bit of time, and it's based on actual coin flipping data. So we did that, and the result came up 21 heads out of 50 flips. Still not quite exactly a 50-50 result, or 25 heads out of 50 flips. The play of the effect of chance has meant that there can be a variation in the result that you get back. Now, that doesn't mean that coin is not a 50-50 coin, that there's something wrong with it. It just means that chance has given us a slightly different result. So the question then that we have is, for every experiment we do, how do we know that the result that we've got is actually due to the result and not just to the play of chance that's finding there? Okay, so we've looked at results that you'll normally see in primary research, as in results of experiments or results of observational studies. But sometimes you'll see what's called a systematic analysis, or a systematic review, or a meta-analysis, which combines the results of several studies that address a related research question or research hypothesis. So a meta-analysis really is the analysis of the analyses that have already been done. So let's say we were looking at mobile phones and ears, and we did our study on that. But let's say that 20 or 30 other studies were also done looking at mobile phones and ears, and they were similar in the type of study design, and they were similar in terms of the outcomes and the exposure. They all used mobile phones, and they measured whether people's ears fell off, I should say. So what if we could take the results from all those 20 or 30 studies and put them together? Now that would give us a far more powerful answer to the question, does using your mobile phone make your ears fall off, in this fictional example? So a meta-analysis is one way to combine, well, it describes how we combine those results of those several studies together. So often, if you see a meta-analysis, you'll see a blobbogram, or this is called an odds ratio plot. Someone might call it that. So here we can see the results of 1, 2, 3, 4, 5 studies here. And each of those studies is represented by a dot which shows the finding of the study, and then a line which shows the confidence interval of that study. And it's an odds ratio, so the plot goes from 1 in the center to less than 1 over here and more than 1 on the other side. So we can see here that for the study, this first study at the top, the result was 1, or very close to 1, and the confidence interval spanned all the way across. So that's really, you could say someone might be disappointed by the result of that study because it's showing really no difference from using a mobile phone to not. Now this study over here was a little bit different. It showed a value of a result of less than 1, the black dot in the middle, and the confidence, or the range of the possible findings from that study, could be anywhere along this black line. And as far as they go, the nearest to 1 is still has not overlapped with this line here of 1, no effect. So this is a significant finding, and it shows less than 1. Over here, we similarly have a study that showed a result more than 1, but the confidence interval has overlapped the line of no effect. So we could do the same protocol, the same experiment, same trial tomorrow, and the result could be way over here. Completely different result. Likewise, this one has an overlapping confidence interval, and this one over here is significant. So with a blobbogram, an odds ratio plot, you'll often see a diamond where the tips of the diamond show the true range of findings after you've aggregated all of these findings together. You've analysed all of this information, and that has resulted in this finding here. So even though we've got a couple of results here that weren't significant in themselves, they've contributed to this overall finding, which is showing some significance because the tips of the end of the diamond are all within this range here, and they don't overlap 1. So that's roughly how you interpret the blobbogram. So now's your chance to do a little bit of group work about blobbograms, and we'll let you carry on with that.